Good day, everyone. Let me introduce first myself. I am Mary Ann Reyes, your teacher in waves and optics. Now, let's start our lesson from periodic motion. Okay, look at the picture. What is in the picture? Have you already experienced it? What is the motion of the object when you push it? Does it move in a circle or move back and forth? These things happen most of the time in our surroundings. The dazzling of leaves, a wrecking ball, a rocking chair, and many more. So these are called periodic motion. Now, what is periodic motion? So periodic motion refers to the motion that is repeated at regular intervals of time. A body undergoing motion always has a stable equilibrium position. The equilibrium position, otherwise known as resting position, is the position assumed by the body when it is not vibrating. Now, we have many examples of periodic motion. So the first one, these are the examples of periodic motion. The first picture, the first picture this is shock absorbers. So shock absorbers are used by vehicles. It moves up and down when the vehicle moves in an unstable road. Another one, we have seesaw. Now seesaw is commonly seen in playgrounds. When two persons ride on each end, they tend to move up and down. So next, this is pendulum. Now, when the pendulum from its original position A will move towards B and C, a restoring force will be at A, where restoring force is a force that tends to restore a body from its displacement to its equilibrium position. By the time it reaches B, okay, so the body has gained kinetic energy, overshoots this position, moves and stops somewhere on the other side C. The body will gain pull back towards equilibrium. Vibration about this equilibrium position results only from the action of the restoring force. So the amplitude of vibration is the maximum displacement of a body from its equilibrium position. This is represented by the displacement from position B to A or from B to C. Now, let's proceed to the period. Now, what is period? So, the period of a body in a periodic motion in the time required to make a complete to and from motion. So one complete to and from motion is called cycle. From A to C and back to the position A is one cycle. Period is always expressed in seconds. Now, frequency. How about frequency? So the frequency is the number of cycles per unit time. Its SI unit is hertz. So 1 hertz is equal to 1 cycle per second. So frequency is the reciprocal of period. Okay, so angular frequency. Sometimes angular frequency, this is your angular frequency, the symbol of your angular frequency. Angular frequency is used instead of frequency. Angular frequency is commonly expressed in radians per seconds. The relationship between angular frequency and frequency is given by this. So angular frequency is equal to 2 pi f, or we have another formula, 2 pi all over t. So the relationship between the angular frequency and your frequency is directly proportional with each other, meaning when angular frequency increases, this frequency also increases. And how about the angular frequency and period? Angular frequency and period is inversely proportional with each other. So when angular frequency increases, the period will decreases. So that is the relationship between your angular frequency, and period. Now let's look for an example. Okay, so an example. An oscillating body takes 0.8 seconds to complete 4 cycles. What is the period, the frequency, and angular frequency of the body? We have this solution. Okay, so T is equal to time all over number of cycles because as we've said a while ago that period is the motion in time required to make a cycle, complete cycle. So we have this formula. So we have to substitute the time is given and the number of cycles is given. Substitute this value to our formula. So T is equal to 0.8 seconds divided by 4 cycles. So our answer will be 0.2 seconds. Okay, how about the frequency? The frequency now, we have the value of time now. So we use this formula. F is equal to 1 all over T. Substitute the given value. 1 all over 0.2 seconds is equal to 5 hertz. Next, we look into the angular frequency. We say that angular frequency is equal to 2 pi f. So, frequency is given now. So, we have to substitute each given value to our formula. The formula, 2 pi, the frequency, the value of our frequency is 5 hertz. Now, 2 pi times 5 hertz is equal to 31 rad per second. That is our final answer for angular frequency. We have 31 rad per second. So, after that, now we will proceed to simple harmonic motion. So, what is simple harmonic motion? Now, simple harmonic motion, like any motion, can be described in terms of displacement, velocity, and acceleration. And this model can be helpful in explaining these characteristics. The model consists of small balls. Small ball attached to the top of a rotating turntable. The ball is moving in uniform circular motion. So this is the movement of the ball. Now, on a path known as the reference circle. As the ball moves, its shadows falls on a strip of film with the paper